All right, welcome to the video for Wednesday, July 1st. Let's get started on the warm-up. Note sort of what I mean down here. So you, by write it as a matrix equation, you should have A is a 2 by 2 matrix, X is just the vector XY, and V is, some values of A and B that depend on the problem that you need to figure out. Okay. So hopefully you've had a chance to pause and look at it, but let's go over the answers. So remember, for this, we're computing e to the 2t, and then we have the derivative of e to the 2t, and then we have e to the negative t, and negative e to the negative t. And we should have negative e to the t, just doing the multiplication, and minus 2 e to the t. And so we should end up with negative 3 e to the t. And this is our answer. All right, so that was pretty straightforward. Here, right, remember we just sort of line up, make sure our variables are sort of lined up into the different rows. We convert it, and we have 1, 5, 2, 7, x, y, equals 1, 3. And that is actually our answer for the first part. For B over here, remember, if A is A, B, C, D, then A inverse is 1 over the determinant of A times the matrix where you swap A and D, and you make B and C both negative. And so if our matrix here is 1, 2, 5, 7, we'll compute our determinant. 1 times 7 minus 2 times 5, so negative 3. And so A inverse is negative 1/3 times 7, 1, negative 2, negative 5. Okay, so having this equation, we multiply by A inverse, which sort of cancels this out, and we get xy equals negative 1/3, 7, negative 2, negative 5, 1. I like to sort of keep the determinant outside until the end, especially if it's like a fraction like that. And then we have times 1, 3. So 7 times 1 minus 2 times 3, negative 5 times 1 plus 1 times 3. So sort of simplifying, we get negative 1/3. That's 7 minus 6, so that's just a 1. And negative 5 plus 3, negative 2. And so at the end, we should get that x is negative 1/3, and y is 2/3. That is our answer for part B. Okay. So today we are going to sort of finish up sort of talking about homogeneous linear equations in general. So we're going to talk about Abel's theorem. Say a little bit more in detail about when you have the fundamental set of solutions. And then we're going to move on to, in the second section, for second order linear equations with constant coefficients. Okay, So to start us off, let's recall sort of what we learned last time. So sort of we closed the last lecture with the following sort of fact. If y1 and y2 are solutions to a homogeneous second-order linear equation, and the Wronskian of y1 and y2 is non-zero. And again, remember, this is non-zero everywhere. Or, I'm sorry, I said it the wrong way. It's not, as long as it is not always equal to 0. So this equals of 0 is like sort of as a function of t. Then we say that y1 and y2 is a fundamental set of solutions to the equation, and the general solution is y of y equals c1 times y1 plus c2 times y2. Okay. To add sort of a little extra fact, like bonus fact onto that, let's say that f and g are both continuous on the interval AB. So, you know, they're defined. We're not dividing by 0 or anything like that for all values in between, you know, some A and B. Then y1 and y2 then if, I should say, y1 and y2 are a fundamental set of solutions, then for all t in between A and B, the Wronskian of y1 and y2 is not equal to 0. Right, that should be strictly in between A and B. Yeah, so this is a really sort of useful fact. So when you're computing Wronskians and stuff, and we're doing this test, so if you can plug in some value that you can plug into f of t and g of t, like if you get 0 out, that means the Wronskian is always 0. So we can like see a little bit more of what this means. So if we look at sort of this equation here, which we've looked at a sort of lot of equations like this, so two possible solutions for this are y equals 1 over t squared and y equals 1 over t cubed. Oh, wait, and I think I should actually change this because otherwise it's not going to be exactly what I want. So let's change this instead of a positive 4. Let's make it a negative 6. Okay, yeah, and then this should have solutions, I guess y equals t, and y equals t to the 7th. Yeah, it should work. Oh no, y equals t to the 6th, I believe. Yeah, t to the 6th. Okay. So first of all, note that this isn't of the form required for this equation, so let's just convert it real quick. So y prime minus 6 over t, y double prime minus 6 over t y prime plus 6 over t squared y equals 0. And so note that f and t, or p of t and q of t, are defined for all non-zero t. Okay. We then have, if we compute the Wronskian of t and t to the 6th, we get 5t to the 6th. And note that the only place where this is 0 is precisely at t equals 0. So this is useful for a couple of reasons. So there was an example yesterday on the worksheet where we were asked to compute the Wronskian. In fact, there were two equations that dealt with this, of Lt and ln of t squared. And in fact, we were also told that these are both solutions. So ln of t and ln of t squared are solutions to y double prime plus 1 over t y prime equals 0. And we could go ahead and check that. But at the end, some people, a fair number actually, which is kind of, I expected, this was kind of supposed to be a trick question. If you didn't remember your logarithm rules, you would get something that was non-zero. So you should have gotten something like, if you didn't use the logarithm rules, you got something like 2 ln of t minus ln of t squared over 2. And note, by what we just discussed, this should be non-zero for all t not equal to 0. So in this case, right, t being 0 is the only thing that can make this not continuous. But if you plug in, say, t equals e, we see that 2 natural log of e minus ln of e squared, you could plug that into your calculator. But right, natural log of e is 1, and natural log of e squared is 2, and so we get 0. So the fact that this is 0 tells us that our Wronskian is necessarily like just equal to the 0 function. Yeah, so that was maybe the caveat that I didn't totally stress. So yeah, so if these are a fundamental set of solutions, okay, no, we're good, we're good. So the fact that this was 0 for E tells us that this is not a fundamental set of solutions. So there's the answer to one of the worksheet problems. And I'll post the whole solutions tomorrow after the people who couldn't attend have turned it in. Okay. So sort of one last fact before we get started on sort of the real topic of the day, and that is Abel's theorem. So what Abel's theorem says is if y1 and y2 are solutions to, again, second order homogeneous equation, then letting W just be a shorthand for our Wronskian of y1 and y2, we have the equation W prime plus P of t times W equals 0. So in particular, if we just move this to the other side, we know we get sort of a linear equation, or really basic separable one. W prime equals something times W. So W is of the form C e to the integral of negative pt dt. And note, there's nothing here about y1 and y2 being, a fundamental set of solutions. If they aren't, but they are, they do have to be solutions, then that C would just be 0. So it handles that case as well. And this also gives you a sort of reason to see why we can't get something 0 here. Really, as long as like pt is 0 or is defined, right? This whole equation can just be represented as e to some power, and e to a power of something is never 0. All right. So let's look, I guess, back at our example. So we already computed this up here, right? We had two solutions, t and t to the 6. We got that our Wronskian was equal to 5t to the 6, and let's just check this. So let's check our work using Abel's theorem. So again, we have to use this form of the equation. If we check this, right, y double prime has a 1 in front of it. So we need to use this equation. So we're told at the end, right, that W is just C times E raised to the integral of negative 6 over t dt. So those cancel. We get with 6 e to the 6 times natural log of t. Canceling out the e to the t and the natural log, we get its c t to the 6th. If we check here, we see that yes, 5t to the 6th does equal ct to the 6th for c equals 5. And so we're checked our work, and so that lets us know that okay, we probably took the Wronskian correct and stuff. So this is a really nice way of checking your work in general, and it's going to It's going to sort of be important for us later down the line. All right. So now let's get into a topic that we're basically going to continue talking about for basically the rest of this section. And we've already talked about it a bit, and that is second order linear equations with constant coefficients. So what does this mean? AKA equations of the form ay double prime plus by prime plus cy equals 0 for numbers a, b, and c. So normally, right, when I write it, we always have the f of t symbol. Here we're just talking about a, b, and c being numbers. Right, give me 1 second. All right. So we have some tools, but let's look at sort of, our sort of first strategy by, looking at an example. So we've already solved a couple of these. And in fact, Abel's theorem gives us another thing to look at. So let's try to find the general solution to this. So as sort of an aside, note that Abel's theorem says that if I take the Wronskian of a fundamental set of solutions, it's going to be c times e to the integral of -9 dt, or c to the e -9t. So one way to sort of think about what we're about to do next, other than we've sort of already studied these and we see that these equations of this of this form work, is let's just look for equations of the form y equals e to the RT. Okay. So again, I'm going to sort of work this problem through in a lot of detail. I'm going to use red pen here for stuff that I don't want you guys to include every time. And then I'll sort of point out the steps that I actually expect to see, because we're going to be dealing with these a lot. It's important that we sort of get to the point where we can solve them pretty fast, so we have more time to work on other aspects of the problem. Okay, so y equals e to the RT, right? So y prime equals r e to the RT, y double prime equals r squared e to the RT. And now we can plug this all in. We'll pull out an e to the RT, and we're left with this equation r plus 9r minus 22 equals 0. And the key thing here is just this polynomial. So this specific polynomial, where we just replace y double prime, y prime and with y double prime with r squared, y prime with r, and y with just 1, which we see we got here, this is known as the characteristic polynomial. So we've seen a couple examples of these already, but like let's just sort of make that jump. We know we're going to have to do these steps like every time, but they're always sort of the same. We just want to now look for roots of our characteristic polynomial. So in this case, we can actually factor this. So negative 22, well, 22 is, can be written as 2 times 11, and positive 11 times negative 2 adds up to 9. And so that tells us that r is equal to 2 or negative 11. Okay. So we know that, we have two solutions, e to the 2t and e to the negative 11t. We should check that these are a fundamental set of solutions. So I'll say in a little bit why you don't need to do this particular part in general. So this is going to be, 2 times negative 11, that's going to be negative 9. So we have negative 11 e to the negative 9t, and then minus 2 e to the negative 9t. So we get as our answer negative 13 e to the negative 9t. For this one in particular, note, this equation, there's no t's here. It's always continuous. So we should be fine plugging in any t value and seeing that it's non-zero. So if we plug in t equals 0, we get a non-zero thing. So it's a fundamental set of solutions. Okay. So because now it's a fundamental set of solutions, we now know that our general solution is going to be C1 e to the 2t plus C2 e to the negative 11t. And this is our general solution. Okay. So let's sort of think about this. So let's look at the Wronskian of, let's say we got somewhere, we were solving these equations, we got e to the r1t and e to the r2t, and we compute the Wronskian. or minus R1. So we get something like this, and just the only thing I want to point out is this is going to be non-zero as long as R1 and R2 are different. So this is why, we're sort of not going to require the check in general for at least equations of this form, right? We can get a little bit comfortable with them. Note, okay, as long as the coefficients of the t here are different, we know we're going to get something non-zero. And so let's just not even sort of do the check. Okay, so to sort of summarize what we can do here. So solving a to the y times y double prime plus b times y prime plus c times y equals 0. So step 1, we have our characteristic equation. This is a r squared plus b r plus c equals 0. So what we want to do here is, find the roots. And, we have a couple different tools for this. We can factor. You could complete the square. Or you could just use the quadratic formula. But the key thing is, if you have two roots which are both distinct and, not imaginary, we get then that sort of our fundamental set of solutions. It's going to be e to the r1t, comma e to the r2t. And then our general solution is going to be y equals c1 e to the r1t plus c2 e to the r2t. All right, so pretty straightforward. Write down the polynomial, find the roots, make the jump to the general solution. Again, what I'm writing down here, this has two caveats that we're going to have to address in a further lecture. The roots have to be real, and they have to be distinct. What happens in the other case we will discuss later on, but let's just do an example. All right. So we can just write down our characteristic equation, minus 6r plus 7 equals 0. You might sort of look like you can factor this, right? We have a 6 and a 7. 7 times 1 is 7. maybe if you change the signs, you could get a 6, but it's just not possible. So let's solve this. Let's solve this by completing the square. So remember, completing the square. So what we want to do is write it av the form r minus a squared plus b. And if we expand this, right, we get r squared minus 2ar plus a squared plus b. So if our a, this needs to be equal to 6r, so 2a needs to be 6, so a is 3. Again, I'm sort of showing this in way too much detail, but we need a 9, so let's add 2 to both sides. And now on this side, we have r minus 3 squared equals 2. Right, we can take the square root. R minus 3 equals plus or minus 2, square root of 2, and r equals 3 plus or minus the square root of 2. Could, of course, also use the quadratic formula, but completing the square can be really useful. Okay, so we have our two roots. So we have our fundamental set of solutions now. Which is e raised to the 3 plus square root of 2 times t, and e to the 3 minus square root of 2 times t. And so now we have our general solution. Y equals e, or c1 e raised to the 3 plus square root of 2 times t, plus c2 e raised to the 3 minus square root of 2 times t. Okay. I'm going to do one more example before I have you guys practice these with some exercises, and hopefully end it kind of early to make up for Monday. So let's solve the IVP y double prime plus 10y prime plus 21y equals 0, where y of 0 equals 3 and y prime of 0 equals 1. Okay, so this is an IVP. I've done a few examples of these, but I still saw some people getting confused about it during our sort of Zoom meeting yesterday. So let's go that. So we can just, characteristic equation again, r squared plus 10r plus 21 equals 0. Let's see, 21, see if we can factor this. 7 times 3 is 21. That adds up to 10, so r plus 3 and r plus 7 equals 0. So that tells us that r is negative 3 or negative 7. So our fundamental set of solutions is going to be e to the negative 3t and e to the negative 7t. And so our general solution is c1 e to the negative 3t plus c2 e to the negative 7t. Okay. So now skipping, or not really skipping, but continuing on to the next part. So y of 0, so this is our y. Well, what's our y prime? It's negative 3 c1 e to the negative 3t plus, or I guess minus 7 c2 e to the negative 7t. So we need y of 0 to be 3, so that tells us that c1 e to the 0 plus c2 e to the 0 equals 3, and y prime of 0, which is negative 3 c1 minus 7 c2 e to the 0 equals 1. Okay, so we want to solve the system. C1 plus C2 equals 3, and negative 3 C1 minus 7 C2 equals 1. So, we can do this a bunch of different ways. Let's just sort of solve for C1, do it that way. So C1 equals 3 minus C2. And we'll plug that in now down here, negative 3 minus C2 minus 7 C2 equals 1. Negative 9 minus 3 C2 minus 7 C2 equals 1, or 10 C2 equals 10. So C2 equals 1, and up back here we get C2 is 3 minus 1, so that's 2. I'm sorry, not C2, C1. And then again, common error, not writing it down at the end, but all we got to do is use C1 is 2, so this is 2 e to the negative 3t. Oh, wait. No, I am off. Okay, yeah, that doesn't match. That should be negative 10 there, giving us a negative 1 and a positive 4. So C1 is 4 e to the negative 3t, and then minus e to the negative 7t, and that is our final answer. All right, so just 2 problems to finish us off. Well, okay, technically maybe 3. But these are pretty easy and straightforward. They don't take long at all. Y double prime to minus 9y prime plus 20y equals 0. Part B. We're going to do y double prime plus 8y prime plus 13y equals 0. And then finally, should end with an IVP, which is y double prime, or solve the IVP, y double prime minus 9, y prime minus 36, y equals 0, where y of 0 equals 7, and y prime of 0 equals 9. All right, so pause here, give these a shot, and then I will go over some of these answers. Okay, so hopefully these weren't too difficult, right? For the first one, I'll just say, right, you should have gotten this as your characteristic equation. And then you can factor this as r minus 4, r minus 5 equals 0, which then skipping, ahead just tells us that y is c1 e to the 4t plus c2 e to the 5t. All right. Next one similar, but the answers don't come out as nice. What you should have gotten here was y is equal to c1 e to negative 4 plus square root of 3 times t plus c2 e to the negative 4 minus square root of 3 times t. And then here, you should have gotten as your general solution y equals c1 e to the negative 3t plus c2 e to the positive 12t. And the particular solution that solves the IVP should be 5 e to the negative 3t plus 2 e to the 12t. All right, so we're going to end it there. Next lecture, we will talk about what happens when we get a repeated root, and then likely start discussing the complex root situation as well.